all our techniques built on top of the previous ones. And now we finally reached the pinnacle of the series, signatures. What are they? How do we find them? And why are they the holy grail of mem scans? Alright, let's start from the beginning. Let's say you want to hack a game and change your money to be 2 billion or something. How could you do that? A really common technique is to take the money value which you currently have, let's say 100, and finding all memory locations which are equal to 100. And once you have those, then you force change the money value, update it to like 99 or something, and then rescan it, filter it out with the new money value, and eventually after few iterations you will end up with one single money value which you can change to 2 billion, and that's it, you hacked the game. It's very good, it's very effective, and that's like one of the main features of Cheat Engine. And we did that in episodes 3 through 5. And it all works until one point, and that is closing the program. After reopening the program, you will soon realize that the money value is no longer in the same exact location, which means you would need to rescan it once again to change it. But we don't want to do that. We scanned it once. We want to access it all the time, no matter when we close or reopen the program. What are we gonna do? Well, this is where .data comes in. .data is a region of your program which is meant for data. It contains all the global variables inside the program. If the code accesses global variables, if the code stores the money value on a global state, chances are it accesses it through memory inside the .data region. It might not be there, the money could be on the heap. It probably is if it's not in the same location. But what you could do is find a link between the .data region and the money value on the heap. And that's a technique called offset scanning. And offset scanning is what we implemented on episodes 6 through 10, emphasis on 6, 8, and 10. And that's really cool. We built that and it's really awesome. And it all works until you reach another critical point, and that is an update. Once the program updates, well, the thing is that the data region can shift. The global variable which you used to find your money value is no longer there. It can be shifted by 1 byte, 2 bytes, or 5 megabytes. It doesn't matter, one thing is certain, is uncertainty. That offset link in itself is probably the same. It's just the global variable which we base it off is different. What are we gonna do? What if instead of basing it on the global variables, we based it on the actual code which accesses the global variables? What if you could find a unique piece of code which does that access and read the offset from that code, and thus, like after an update, it would stay the same, because that code, chances are that particular code is not gonna change. Everything else around could change, but as long as that code doesn't change, it's fine. All the code is stored in .text region, which consists of low-level CPU instructions, and they're encoded in bytes. One single instruction is not unique, but if you string enough instructions together, you will get a unique sequence of instructions, and that exactly is a signature. A few things are very important: uniqueness, shortness, and updatability. Another thing we have to do is mask out bytes which are at risk of update. That are all the function calls, all the function branches, and all the moves from global variables. Those have really high risk of changing. And what we're gonna do, we're gonna mask them out, change those places into question marks, and those places we will match anything to them. Also, before we continue, don't forget to overflow the like button. You know my goal, -2 billion likes, but that first involves going past 2.147 billion likes. Also, this is a new format, so post in the comments below what you think of it. Anyways, with that out of the way, What are we gonna do in this episode? We're gonna build on top of our offset scanner, global scans, etc., and build a signature maker. We're gonna take the global variable which we want to target, and we're going to go through the code and find all the places where that global variable is accessed, and we're gonna create a code signature for all these places. Actually, we're gonna try to find the shortest, the first match, which is like completely unique. And once you have that, you will be able to constantly scan for that particular signature and constantly find it after update. It will be perfect. And that's really cool, but how are we gonna do it? The technique for finding signatures is rather simple. You can extend it, and I will mention the extension later on. But the basic principle is to start from where you want to create a signature, going instruction by instruction and extending it, and then scanning all memory regions, all the code for matches of that signature. If there are no matches, voila, you've got a unique signature. This is essentially it. Now it's time to finally go ahead and implement it. Alright, so I'm gonna skip through the boring stuff. I already defined a command for Sigmaker, which takes one argument, which is the address to the global variable which we want to find the signature to. If it parses correctly, it calls a findSigs function, which takes in a process, a disassembler module, and the address which we just parsed. And the Sigmaker module, it doesn't have anything inside it. It doesn't store anything. It just has this findSigs function which returns a vector of strings. So now we just need to fill in the blank. Essentially, first of all, we need to do some sanity checking. So we're gonna check if the target global is, inside the disassembly module. And we're gonna take all the references from the disassembly module. We will use this inverse map, which is global variable maps to all instruction addresses which point to this global variable. That's the inverse map we're gonna use, and it's very, very useful, I'd say. So what we're gonna do, we're just gonna go and try to get those addresses. It will be disasm.inversemap.get, and we have the target global. And if we don't get it, that means we passed an invalid global variable, so it will be an invalid global variable. The next step is to find the module where our global variable resides in. So it will be module equals process dot module list. We convert it into iterator, and we find where the target global is within the base and the end. So it will be m.base. m.base is less or equal to target global. Base plus m.size is higher than the target global. And if we fail, we will just return, because we want to limit our signature scans within one specific module, because that eliminates a lot of search space, and that allows us to also have shorter signatures, because while one module could have one signature that is unique to the module, but it could exist in other module, and we're only concerned with one particular module where the global variable resides in. That's about it. Now we need to parse the sections to find only executable regions of the module. So it will be the same as in the disassembler module. We don't steal, we just borrow the same code from the disassembly module. So it will be all that, the same stuff, essentially. And this will be ranges, because we don't want to go through the sections, we just want to know the sections. So it'll be that ranges, a vector of starting address and the size of the range. And we map, which will be as.virtualaddress.into and as.virtual size as usize, and we collect those in. Once we have the ranges, now we need to actually prepare our buffers for sig scanning. So what we're gonna do, we're gonna go through all these addresses and read up to 128 bytes of memory for them, because what we're gonna do, we're gonna create a decoder right here, which will decode the instructions, which will will use for creating the signature stuff. So what we're gonna do, create the buffers, which is going to be a vector of arrays of U8 max sig length addresses, iterator, map. We map nothing, we don't use it, we just create a buffer with the length of addresses we've got. So it will be a simple 0 initialized array. We're gonna read memory at those addresses for our buffers. So we're gonna create a so-called read list, which is a new thing for memflow. It's a very, very efficient way of reading multiple things at once. So it will be a read list. It's also going to be a vector, buffs, iterator, mutable iterator over these buffers, and we zip them up with the addresses dot iterator, and we map the buffer and address, we map it into a virtual read data of address and buffer, and we collect that in, and that is done. And what we need to do now is initiate the read. So it will be process.virtualmemory.virt read raw list, and it will be just a mutable reference to read list, and we allow partial results. Now we need to create states for our individual sig scans. So we will create a structure, which is a private structure, Sigstate. And Sigstate, it will hold a few things. It will hold the buffer, a reference to the buffer. So we need to use a lifetime. So for lifetime, we need to create a generic structure which accepts lifetimes. We're gonna have a decoder with the same lifetime, and we're gonna hold instructions, which will be a vector of instruction and its constant offsets. I will talk about that later. And once that's done, what we need to do is we're gonna create states right here. Actually, we could improve this hell a lot by just mapping address right here. I believe that would be a much better approach. And we don't zip it up if anything, we just have a simple A and B, A and B. Yeah, this works. So it will be states equals buffs dot iterator dot map. We've got start IP and we've got the buffer. And what we're gonna do, we're gonna create a decoder. Decoder equals decoder new, which goes a bitness, which we need to define. It takes the buffer and it takes no decoder options essentially. The bitness is as simple as process architecture, and we take the bits and convert that into whatever this accepts, which is probably U32. And once you've got the decoder, we're just gonna do decoder.set IP to the start IP, and then we're gonna do Sigstate. We pass buffer, we pass decoder, and instructions is an empty vector. And we just collect this in, and booyah! Oh, start IP.add U64. Here we go. We need to specify that this is a vector. And now we're gonna write the actual loop for our Sigmaker, the grow phase. So I'm gonna first write the code and then implement it. I'm first gonna write the loop and then I'm gonna implement it. So it's gonna be while we don't have any unique matches, pass through states, we pass through process virtual memory because we're gonna scan stuff, we need virtual memory access, and we pass the ranges for the ranges we need to scan. We're gonna go through for state in states.iterator mutable iterator, and we're gonna do as.add single instruction. But here's what we want to do. We want to break out of the loop if no states add an instruction. So we make this function return a boolean. So if we successfully add an instruction, we set added equals true, which is a flag. If we succeed with at least one state, we set this flag to true. If we don't add an instruction in any iteration of this loop, we just break out of it. And that's the essence of this. So we're gonna first define add single instruction, implement Sigstate, and it will be fn add single instruction, takes mutable self and returns a boolean. If not self.decoder.can decode, we return false. What we do is self.decoder.decode. We just decode an instruction. Now we're gonna check if instruction code is code invalid. We're checking if it's a valid instruction. If it's not valid, we return false. Else we go self.instructions.push the instruction. And we need another thing, which is self.decoder.get constant offsets and return true. Get constant offsets will contain a really important piece of information, and that are the offset within the instruction for all various memory addresses and their sizes. That's what get constant offset has, and that's what we need. It's very, very important. We have this anonymously implemented. So now we need to implement the function for has unique matches. So as unique matches, it takes a few things. It takes states, it takes a virtual memory, which will be for mutable implementation of virtual memory. It takes ranges. We will use virtual memory, so it will return result of boolean in case virtual reads fail or not. So what this function needs to do, it needs to take signatures from the Sigstate and scan all these ranges for, well, the signatures matches. And there's a really important thing that we need to take care of, and that is actually getting the signatures. For signatures, we have two pieces of information, the bytes and the mask. So we need to mask them out, and I think the best place to mask them out is in Sigstate itself. And the mask, you could have it as a boolean, or we could just use a bytes of U8 for mask. So it will be mask vector of U8, and it will be a value of 0 or 255, which is 0xFF, with all bits set to 1. So we have the mask, and we will actually use the constant offsets right here, constant offsets, and we will need the constant offsets right here and now. So that constant offsets equals, and right here, what we need to do, we need to push to the mask, so it will be, we just take the same number of bytes as there are in the instruction and pass them in as 0xFF into the mask. So instruction mask will be a mutable reference to self.mask, and we iterate from self.mask.length minus instruction.length towards the end. And that will take just the end of the mask, which is the bytes we used, without any extra allocations. And then we just call self.mask instruction, and then we pass through instruction, constant offsets, and the mask. And this function, we will implement it right here. So first of all, we need to mask out all memory reads that are based on no instruction, a relative instruction pointer, or like any segment-based register. And afterwards, we also need to mask out every single branch that goes outside the function bound. So it will be all big branches that use 4 bytes as offset, and all the call operations and stuff. So first of all, let's handle memory. We need to use instruction memory base and match it to a register. So it will be if register EIP equals instruction.memory base. Then we will call a function which is self-mask mem, and it will be offsets and mask. Those are the two informations that it needs. So this function will actually perform the masking, and right here we need to match whether there are registers which are the memory base is based on. So it's not just EIP. We also have a register REP. We have a bunch of base registers, so it will be ES, CS, SS, DS, FS, GS. And we also need to match no register. And once that's done, it calls the self mask mem function. It will be, we don't need self. We don't need self right here either. Self mask instruction. And mask mem, it checks for offsets.has displacement. I'm not exactly sure what the displacement means, but every instruction that reads memory, it has a displacement which has an offset within the instruction and the size of the memory address that's contained within there. So it will be offsets.displacement offset, and let size equals offsets dot displacement size. And we need to mask all these bytes from offset to offset plus size with zeros. Mask.iterator meet.enumerate if index is higher or equal than offset and index is less than offset plus size, we just set the byte to 0. And that's the mask memory. Now we need to mask out the code. So it will be a very similar thing. Instead, we match operand kinds. So instruction has opcodes and it has operands, which are like, for instance, the memory operand for memory address. But it also has operand for like branches. So it will be operand kind near branch 16 and equals instruction.try operand kind 0, the 0th operand. Why we do the 0th? Well, all the branches, they use just one operand for the branch target. And the same story is here of near branch 32, near branch 64, far branch 16, and far branch 32, although these two instructions in particular are not really used at all. But we just keep them because we can. So it will be self-mask branch. We need to mask all the branches that go beyond the function call. And if you have jumps within the function, chances are there will be one single byte jumps. So we need to like pass an argument for highest branch that's unmasked. This will allow us to have much shorter unique signatures if we allow jumps within the functions. It's actually gonna be the same thing, and it's just gonna take unmasked branch size if offsets has immediate. Immediate is the branch value, immediate value. They're stored not in memory, but in immediate value. Actually, the same thing right here, except it has to be not displacement, but immediate. And here we check if size is higher than unmasked branch size. And that's it. Now we have the masking done. There are 3 errors. Sigstate, it needs mask. It will be an empty vector, and this returns a boolean. Oh, we need to back to this function. There will be an issue if we do a while loop, because it will check has unique matches for an empty instruction, and we don't want to do that. So we change this to be a loop, and it will be if not added or has unique matches, then we break out. In this code right here, we will output a list of signatures, and mute out will be a equals vector, an empty vector of signatures, and we just return that. Right here we'll have a out will be a mutable reference to vector of strings. At this point we need to implement has unique matches. So here we will do a really typical scan type thing. So we will just borrow code from, for instance, value scanner. It's going to be a very simple loop. For address and size, instead we will iterate ranges, and we go ahead and we define a chunk size, 4 kilobytes, let's say. Chunk size plus the maximum signature length, so it will be max sig length minus 1. And now we go through ranges, we step up by chunk size. We read right here at address into a buffer, into that particular buffer. So at this point, what we need to do, we need to go through the windows, buffer.windows of max sig length, and we need to enumerate it. Then we have this window. We will create a new address equals address plus offset. And now we need to go through every signature. So we go through bytes, unmask, in states.iterator.map and we map through as.buff and as.mask, and this will be a reference to it. So at this point, we need to do two things. We need to go through these bytes and mask them out and compare them to the window, which also is masked out with this mask. So we need to go, well, let's just create let window.iter.zip mask.iter, and we map it by window mask, and it will be window apply masked with a mask, right? And now we create a bytes iter, it will be bytes.iterator. We zip them up, and then we just compare windows iterator equals bytes iterator, and we need to check the start IP. So it will be and address not equals, well, we need start IP as the start IP, not equals start IP. We have to mark this as somehow mark as duplicate found. We need to do .echo for iterators. There we go, ranges and vert mem. So we need to mark this as it has a duplicate. For that, we will unfortunately need to do an allocation, which is okay because we allocate buffer right here as well. So we will instead create mutable sigs equals map this like so. We map this and we will have a 0 right here, and we don't collect it into a vector. And now we will just have a dupe matches, and we iterate through sigs.iterator mute. Can we borrow this as mutable? Maybe. And we will just do dupe matches plus equals 1. No, we can't. Fortunately, I have to do it like so, and we need to check it like so. Now, the final step is to go through these sigs and collect the ones that are unique. So it will be just, it has unique. We don't have unique matches, and we return as unique. We don't care about start IP. We go through buffer mask dupe matches in sigs, and then if dupe matches equals 0, we mark has unique equals true, and we push a simple bytes to string, which will be a function which takes a buffer and the mask and creates a string pattern which we will like know about. That's a really simple function. It will be bytes to string, it takes bytes and outputs a string, and that will be as simple as bytes.iterator.zip with mask.iterator, and we map it to a simple bytes mask. If mask equals 0, we just pass in through a question mark dot to string. Else, we format this out to be a hex with zeros at the start, and we just collect this into a vector, and we join this together with spaces, and we have an error. Where do we have an error? Oh, obviously, I'm blind. And here we go. We just Rust format everything. And that should be it, theoretically. Let's see if this works. Alright, I'm back. I've got one question for you. Shall we? Too late, let's go. So we just go cargo run release. We have our system right here, which I believe will work. It is out of memory, but we don't care. We just scan i64-100, 98. After scan, yes, 0, 32, 5. We need to sig scan this, not this. Here we go. And we found a signature. We found just one signature, which is this one. Globals. We can sig scan this. We have this signature. Let's say, what if we sig scan this? There is no matches. 58. Here we go. We found this signature, which is for this global variable. And that's, I believe that's pretty cool, I'd say. That's pretty fantastic. That's it. We did it. So I will just walk around like one bit of code that is really that I don't think I explained well enough, and that is this has unique matches. What it does, it creates this temporary vector for signatures, which like takes the buffer, it takes the mask, and it creates this temporary variable for duplicate matches. Duplicate matches initialize to 0 because what we do right here, we read all these ranges, and we go ahead, we read them, we go through them, we read them, then we create a windows of max sig length, which is 128 bytes, I believe, right here. Once you have that, you go through the windows, and you go through each signature, you go through each byte of the code, and then you check every signature on that byte, and then you compare the two. The signature could be shorter than 128 bytes, but the reason this works is because we zip up the window iterator with the mask. Bytes are zipped up with the mask, and what zip does, it takes two iterators and it like creates a tuple out of them, and it ends whenever one of the iterators ends. So it will be the shortest iterator, so it will have the length of mask, and mask is always with the same length as the number of bytes we have decoded, because we extended right here the mask, and then we mask it out and we push the instructions. And that's essentially it. Now, I mentioned at the start that there is an extension which you could make, and that is another phase built on top of this, and it's like a shift shrink phase, which we would basically reach this point and then we would try checking the bytes behind. Maybe there are some bytes behind the start of the signature that will create a unique signature that is shorter than the current one. But that is very much optional. The basic idea right here is this. But if you want to see that video, pop down in the comments below that you would love to see that, so I can know that I should make it. But other than that, I think this episode is done. We actually have just 2 episodes left. It would be multi-threading and the finishing touches. But this was it. This was signatures. I hope you liked it. I hope you understood what I wrote here, and I hope this was informative. Don't forget to overflow the like button, hit subscribe for more content like this, and I'll see you later. Don't forget, my name was Heap, yours was undefined. See ya.